It's time we talked about loop quantum gravity. What exactly is it? What are the loops? And can it really defeat string theory in our quest for a theory of everything? The holy grail of physics is to connect our understanding of the tiny scales of atoms and subatomic particles with that of the vast scales of planets, galaxies, the entire universe. To connect quantum physics with Einstein's general theory of relativity. Our search for a theory of quantum gravity is a century old, and we've talked about it quite a bit already, including what's probably the lead contender, string theory. But string theory isn't the only game in town, or so some physicists believe. There may be another way to reconcile the physics of the tiny and the gigantic, another way to a theory of quantum gravity that avoids a lot of the conceptual baggage, like tiny wiggling strings made of coiled up extra dimensions. That other way would be loop quantum gravity, and today we're going to find out exactly what it is. Back in the day, we talked about why combining quantum mechanics and general relativity was so hard. For example, there's the fact that general relativity, or perhaps quantum mechanics, breaks down when we think about the extreme densities of the black hole or the Big Bang singularities. But there are more fundamental conflicts, namely background independence and the problem of time. Now, I'll mention the problem of time briefly in a little bit, but the real focus is going to be on this background independence thing because this is what really inspired the invention of loop quantum gravity. So, what is it? Quantum mechanics, and indeed most theories in physics, involve a set of equations describing how stuff moves around, exerts force, etc. on some background coordinate system, like actors on a stage, where the actors are particles and wave functions and fields, and the stage is the coordinates of space and time. In quantum mechanics, that stage is flat and static and isn't influenced by the actors. It requires some giant hacks to even attempt regular quantum calculations in a non-flat geometry. In short, quantum mechanics is not background independent. General relativity, on the other hand, has to be background independent because that's what its equations do. They change the background. They describe how the presence of mass and energy warp the fabric of space-time. Our background coordinate system itself becomes a dynamic entity. More precisely, the metric, the object encapsulating the geometry and causal structure of spacetime, evolves in the equations of GR. So those equations need to work regardless of that background. In string theory, a type of background independence emerges in an abstract space of moving strings, and with that comes a gravitational field. But for that to work, first you need those strings to exist, and we don't know if they do. Loop quantum gravity tries to quantize general relativity with no strings attached, while preserving the background independence already inherent to GR. But why is quantizing general relativity so difficult in the first place? The challenge really gets us to the fundamentals of what a quantum theory actually is. So just quickly, let's review all of quantum mechanics. In classical physics, we have variables like position, time, momentum, energy, mathematical expressions that represent the observable properties of the object or system that you're trying to describe. Some of these, say position and time, also form our background coordinate system. But in quantum mechanics, things aren't so straightforward. Certain properties have an inbuilt uncertainty and only take concrete values after measurement. Absent measurement, they exist in a fuzzy space of possibilities called a wave function. In the first formulations of quantum mechanics, that wave function describes the distribution of possible positions and momenta of, say, a particle. These can be resolved into concrete measured values by acting on that wave function with so-called position and momentum operators. The wave function and operators are fundamentally tied to the coordinate system. After all, the position and momentum of quantum mechanics literally describes the location on a spatial coordinate system and the change in that location over time. That makes it highly background dependent. There are other ways to formulate quantum mechanics like quantum field theory, but these ultimately have the same issue. And it gets worse actually. In quantum mechanics, time is treated completely separately to the other variables. There is no time wave function or time operator. This is completely at odds with general relativity, in which time is treated as just another dimension. This is the so-called problem of time that I mentioned, and it's strongly connected to background independence. A quantum theory of gravity needs to fix both of these issues, but we're going to focus on background independence for now. The equations of quantum mechanics let you calculate changing properties of a particle like its position or momentum relative to the background coordinate system. The equations of general relativity let you calculate the changing shape of the coordinate system itself, encapsulated by the metric. So maybe instead of thinking about quantum fuzziness of position and momentum, we can think about the quantum fuzziness of the metric itself. And instead of an equation that describes the quantum evolution of the properties of an object in space-time, maybe there's an equation that describes the quantum evolution of the geometry of space. Well, there is, or at least an attempt at one. It's called the Wheeler-DeWitt equation, and it's based on something called ADM formalism. ADM starts by defining this abstract space of spaces, 3D spatial metrics, 3D spatial slices cut out of 4D space-time. It then gives a sort of equation of motion for how these metrics evolve through time. You can imagine a funky coordinate system describing where you are in this abstract space of metrics. As you move through this coordinate system, the geometry of space changes. You can also imagine analogies of position and momentum in this space of metrics. So, the Wheeler-DeWitt equation quantizes these, turns them into quantum operators. The result is a quantum equation for the fabric of space, a contender for a theory of quantum gravity. The Wheeler-DeWitt equation was promising, but it turned out to be unsolvable, which makes it not so useful and impossible to verify as correct. So perhaps this whole path of using abstract coordinates is a dead end, or perhaps we just haven't gone down it far enough. That's what loop quantum gravity does. It takes us down the abstraction rabbit hole, past our space of metrics, into a space of something called connections. And these connections are going to give us our loops. Connections are mathematical functions that tell you how something like a vector changes as it moves between 2 points in space. We saw an example of this way back in the day when we looked at parallel transport. As you move the base of a vector along a path in curved space, the vector rotates, and the amount of rotation encodes information about the changes in geometry along that path. If connections contain all of the information about space-time, then maybe we can represent space-time with these connections instead of with regular coordinates. In the 1950s, Einstein himself tried to rewrite general relativity in terms of these parallel transport vector connections, but the result was a mess. The breakthrough came in the 80s, when Abe Ashkatar tried to define a different type of connection, one in which you parallel transport not a vector, but something called a spinor, a vector-like thing that also represents a quantum of angular momentum, or spin. Ashkatar rewrote general relativity in terms of these spin connections, now known as Ashkatar variables. In this formalism, the space of metrics looks just like a space of fields in quantum field theory. Quantizing gravity suddenly looked to be in reach. And now we get to the loops of loop quantum gravity. Lee Smolin and Carlo Rovelli realized they could fully solve the Wheeler-DeWitt equation by representing spatial metrics using Ashkatar's spin connections. But they needed one more trick, one layer deeper in abstraction. They evaluated these connections over closed loops, so each point connected back to itself. They realized it was possible to define any geometry in 3D space out of a sort of weave of these closed loops, with each loop like an elementary closed circuit of gravitational field. So now you have a space of loops with which to construct the fabric of space, and that space of loops can be quantized rather neatly. and in a background-independent way. After all, there is no background until these now quantum loop states build it. The result, of course, is loop quantum gravity. It's general relativity, our modern theory of gravity, cast in terms of very abstract building blocks, not with chunks of space-time, but with quantum circuits of gravitational field. 3D space can be sort of woven from these loops into something called a spin network, which is a concept too abstract for even this episode. But the resulting 3D space looks normal on large scales. It looks like space. But on the tiniest scales, the Planck scale, it's sort of pixelated. At the nexuses of this weave, you have quantized volume elements, irreducible grains of space, connected by quantized area faces like facets. But even that description is probably too space-like. Probably the underlying weave of the fabric of space doesn't resemble anything intuitive at all. The big success of loop quantum gravity is that it manages to combine general relativity and quantum mechanics in their currently accepted forms without taking away their most important foundational principles, and without adding big assumptions like the existence of strings or extra dimensions or supersymmetry. The theory has some other successes. For example, the theory seems to predict Hawking radiation and black hole entropy consistent with Hawking and Bekenstein's equations. However, there are also many who identify serious fundamental issues with the theory. While LQG has background independence in terms of different 3D spatial geometries, it's not actually clear that this independence extends to 4D space-time. And connected to this, LQG doesn't solve the problem of time. More generally, for this theory to be successful, it needs to give you the equations of good old general relativity on large non-quantum scales, in the so-called classical limit, but it's not clear that it can do that. This is still a hotly debated topic. Some researchers think that the method and foundations are sound, and that the current criticisms and shortcomings can be resolved with more research and extensions to the existing formalism. Others argue that the problems are fundamental and that no amount of tinkering and extending will resolve them. A lot more exploration is needed on the theoretical side, but what about experiments? Surprisingly, some experiments have actually been proposed. Loop quantum gravity seems to predict that the speed of light should depend very slightly on the energy of the photon, with, for example, high energy gamma rays traveling a wee bit slower than low energy radio waves due to the way they propagate through the graininess of our loop quantum gravity spacetime. This was tested in 2009 by looking for differences in the arrival time of light from a gamma ray burst nearly 1 billion light years away. If there was any difference, it was barely measurable, and that doesn't look great for loop quantum gravity. Loop quantum gravity is an intriguing alternative to the more popular string theory. Both currently live deep in their respective theoretical rabbit holes, not yet able to make experimental contact with the real universe. But the mathematics have yielded intriguing clues to the nature of the fabric of the universe, and that nature is very weird. One way or another, we live in a seriously loopy space-time.